More from homework 28, 15, and 17. For these problems, you needed to find where f is increasing, decreasing, relative minimums, maximums of f, concave up, concave down, and points of inflection. So I'm going to talk through the derivatives that I've taken and the simplification process, because that's really the biggest issue. And I'll highlight as I go along. So taking the derivative, right now I'm working on 15, taking the derivative of e to the blah. Derivative e to the blah is e to the blah. Baby is 2x, so plug the baby in, multiply by the derivative of the baby 2. Then plus derivative of e to the negative x is derivative of e to the blah. E to the blah is the derivative, and then plug the baby in, multiply by the derivative, -1. And then I just simplified that a touch by changing the multiplication into just subtraction. Now, from here, I took the second derivative, and then I'll go back over and go through the simplification. But it's good to take that second derivative while you're in the rhythm of this particular function, because you should see that if you take the derivative again of e to the 2x, you're just going to get again 2 times e to the 2x. So you're multiplying this 2 by another one. And then if I take the derivative of e to the negative x again, as I did before, I will be getting the negative e to the negative x. So I'm multiplying by another -1, making it a positive. And so I get the second derivative here. I'm going to go through the simplification of the first derivative first, and then I'll hit back over here to the second derivative. So negative exponent means it's in the denominator as a fraction. Then I need to get a common denominator, and that would be done by multiplying and dividing the left term by e to the x. And when I multiply e to the 2x times e to the x, I add the exponents, 2x plus 1x, to get 3x. So that makes my numerator 2e to the 3x minus 1 over the common denominator e to the x. Now, I need to find my critical numbers. That means anywhere that the numerator is equal to 0, or also anywhere the denominator is equal to 0, because that would make it undefined. The thing about e to the x is it's never equal to 0. So the denominator is positive at all times. So I set the numerator equal to 0, and I added 1 divided by 2. And then to undo natural log, I need to to undo e to the power of, I need to bring in its inverse function, which is natural log, understood to be log base e. I take the natural log of both sides, and that causes these two to cancel each other out and leave just the 3x, and equal to natural log of 1/2. So x ends up being the natural log of 1/2 divided by 3. Now, it's good to be aware that if you take the natural log of a number between 0 and 1, it is a negative number. If you think about the graph of a logarithm, that's a mediocre graph, but x-intercept 1, if you plug in any x between 0 and 1, your y value is negative for your logarithm. I also saw that the textbook rewrote this, and let me just make sure you're clear how it's the same thing. Let's use black. All right. So the natural log of 1/2 is the same thing as the natural log of 2 to the -1 power, and then over 3. And using a log rule, the exponent -1 can multiply in front to be negative the natural log of 2, and then divided by 3. So same thing as what the textbook was using. You can use either this form or this form. Now, I need that one number is my only critical number, and I need to figure out where the derivative is positive and negative. That means I can plug any number into the x of my derivative, plug in any of these numbers that is smaller than the natural log of 1/2 divided by 3, and see if I get positive or negative. Well, let's look at what we are actually working with. The denominator is exponential. Just plain that it is positive at all times. So I just need to focus on my numerator. And sometimes it helps just to go big. Can you think of a negative number that is so far down the negative arena, it's just way out there? Negative a billion. Let's say we go with that. If I'm plugging in negative 1 billion into x, multiplying it by 3, and then putting it into an exponential function, do you realize how small that is? It's a very, very small positive number. Let's remember the graph of e to the x, it's a base greater than 1, so it's an exponential growth, y-intercept 1. So when I am looking way down in the negative area, I have an asymptoting function that is positive but so close to 0 it's ridiculous. So this is insanely small number, minus 1, insanely small positive number, I should say. That's going to be negative. So that gives me negative for when I am less than natural log of 1/2 divided by 3, whatever that crazy number is. Now, go big the other way. Think of some ridiculously large number, or maybe even just think, what does e to the x do when it gets ridiculously big? Because whatever I choose for x that is larger than this number, I plug it in here, I multiply it by 3, and I have really big x coordinate going in exponential. Super big number. Multiplied by 2, and then minus 1. That minus 1 is doing nothing to this insane positiveness of positivity. So I end up with a positive value for my first derivative for anything I plug in that is larger than this number that happens to be the natural log of 1/2 divided by 3. So now I am able to answer where is f increasing and decreasing. F is increasing over the open, and I'm not going to bother including endpoints. Over the open interval, natural log of 1/2 over 3 to infinity. And technically it includes the endpoint due to the definition of increasing versus decreasing. And decreasing where f prime is showing up negative, which technically does include this point, but I'm just going to leave it as an open interval. And then for relative minimum maximum, if the graph goes down and then up, relative minimum. But I only know my x coordinate from this information. My x coordinate is the lovely natural log of 1/2 divided by 3. And I need to find the y value from the original function. So the original function is e to the 2x plus e to the negative x. E to the 2x plus e to the negative x. So I got to throw this number into this lovely little mix here. This is where it might actually be nicer to change the natural log of 1/2 into negative the natural log of 2. Just saves some fractional nightmares. So if I take this and plug it into these x's, I am going to get e to the power of negative 2 natural log 2 divided by 3. And if you like, that 2 multiplying in front can become an exponent, making this negative the natural log of 2 squared divided by 3. Yeah, that's not so pretty. Anyway, I still have another exponential, plus e to the power of negative x, so basically e to the natural log of 2 divided by 3. And, you know, at this point, it's a number. And let me see, the textbook, did they put that in a tidy little value? Boop. Yeah, it looks like they didn't. They ended up just saying, oh, they did get it a little bit farther than this because I do have e to the power of. So let's go a little farther, shall we, for fun? So negative multiplication turns into a negative exponent. So that's actually the natural log of 1 divided by 4 because it's 4 to the negative 1. That 3 is a problem though. In order to rewrite this the way that the textbook has it, you need to actually condense all of this into a nice little logarithm, and then e and log will cancel. So that means that I really have, this was an exponent of negative 1/3 natural log 4 with e as the base. The log rule says that this becomes an exponent on the 4. Once that happens, you have e to the power of natural log of 4 to the negative 1/3 power. These cancel, and you end up with 4 to the negative 1/3 power, which is really the cube root of 4 in a denominator. Then the plus part. This is e to the 1/3 times the natural log of 2. I can make the 1/3 become an exponent inside my logarithm. So it's 2 to the 1/3 power. And then e to the power of natural log can cancel each other out, and I have plus, and now it's 2 to the 1/3 power, which is the cube root of 2. And I believe that is the point where the textbook finally said, maybe no more. Oh, they did simplify. Well, okay, let's just call that enough. And the textbook got that this was approximately 1.89. Yeah, but anyway. All that work. Yeah, sometimes you do just want to use a calculator. Okay, that was first derivative. Second derivative. I again took my negative x and wrote it as a positive exponent for a denominator. And then I took this 4e to the 2x, and I'm trying to get the common denominator with e to the x, so I multiplied by e to the x and divided by e to the x. And e to the 2x times e to the x, I add the exponents to get e to the 3x, and then I have my common denominator, and 4e to the 3x plus 1. E to the x is always positive. So I need to find out what makes 4 times e to the 3x plus 1 equal to 0. And then I begin to isolate my exponential. I subtract 1 and divide by 4, and I wind up with an exponential function is equal to a negative number. Now, if you look at exponential functions, just a basic hi, I'm e to the x, only positive numbers come out of it. If I multiply the x by a 3, all I'm doing is horizontally stretching the graph. That's not causing the answers to be any different than they're all positive numbers. So an exponential function can never be equal to a negative number. That means you don't have anywhere that the second derivative is equal to 0. All that work to discover there are no points of inflection. And if you just pick any number you want and plug it into x, all you need to know is positive or negative for the whole shebang. Well, exponential functions only are positive. So positive number times 4 plus 1 divided by positive number, The second derivative is always positive. Therefore, it is concave up for the entirety of its domain, which is all real numbers. It's never concave down. There are no points of inflection. Did you enjoy all of that just to find out that it's just always positive? Those are always the amusing moments that my students don't say are as amusing as I think they are. So anyway, all right, number 17. Here is my taking of the derivative, quotient rule. We've got our low, so low d high minus high d low. Square the square root to get x, and away we go. And now simplifying, I'm going to erase some of that because it looks a little messy to me. Oh, it's not going to let me just erase, is it? Okay, well, I'm going to have to live with it. So I have root x times 1 over x. And if you want, you can see it as this is x to the 1/2 times x to the -1. I add the exponents. 1/2 plus -1 gives me -1/2, and I wind up getting root x in the denominator. Then I have minus. My natural log x is hanging out. And then I have 1/2 x to the -1/2 becomes 2 root x in the denominator. And I need to get a common denominator of the numerator's fraction. And luckily, I'm not too far away from that. So if I multiply by 2 over 2 to that left term, I will end up getting 2 and then minus natural log x over their common denominator over x. When I combine this denominator of the numerator with this denominator, they end up multiplying in a singular denominator. Now, I'm trying to find what makes this equal to 0. So, what makes 2 minus natural log x equal to 0? I also have an issue of undefined at x equals 0. Because that's what makes the denominator 0. But if I'm dealing with a logarithm, I actually kicked this problem off with half of a domain. What I mean by that is half of the real numbers were in the domain. So if I have the function natural log x, and you know root x doesn't help any either. Only positive numbers go into a logarithm. So I have to have a domain of positive numbers. And then square root has to be non-negative, and it's a denominator, so it can't be 0. So just overemphasis on my domain is only x greater than 0. So when I run into this denominator is giving me undefined at x equals 0, that's not even in the domain in the first place, so it's not a critical number. That means that the only things that can be a critical number have to be positive numbers. So let's see what happens when we set the numerator equal to 0. First, I added natural log x to the other side, and then I undo natural log by e to the powering, e squared equals x. That is a positive number, so that is the domain of my function. When I go to interpret things about f prime, I want to make sure I'm sticking within the domain. So I'm going to put a little open circle here with 0 and a number line showing that the domain is not including 0 all the way to infinity. E squared being a positive number, my only critical number. From here, I need to figure out positive, negative, for the first derivative of x, and I have to pick something between 0 and e squared that I can decently figure out positive or negative. And you know what? Let's save some time. That the fact that the domain is positive numbers only, and you look at this denominator is positive at all times. So ignore it when it comes to finding the sign of f prime and focus on just the numerator. Now, what would be a nice number between 0 and e squared that I can plug into e? Natural log, I mean. And that would be e. E is a good test number. So if x is equal to e, well, it's not there, but you know, somewhere around there, then 2 minus the natural log of e. Natural log of e is 1, so I'm getting a positive number for one of the members of that interval. All the members of the interval are positive. I need to pick a number greater than e squared. And if I want to make my life easy, I can pick e cubed or e to anything that I want that's bigger than 2. So let's say x is e cubed, and I plug it in. I will wind up getting 2 minus 3, which is negative. Or you could realize that if you plug in a large enough x, which we've got large enough going there, if I plug in a large enough number into x, natural log will grow. Slowly, but it will grow. 2 minus something that's going to keep growing and getting bigger, definitely negative. So I can now conclude that my function f is increasing from 0 to e squared. And again, I'm not going to include my endpoint for my increasing, decreasing. F is decreasing if I am larger than e squared onward to infinity. And then I have a relative extrema. And if I look at the fact that I go up followed by down, that's a max. So I have a relative maximum. The x-coordinate is e squared. I need the y-coordinate. To get that y-coordinate, I have to go back to the original function. The original function was natural log x over root x. I'm going to write that down over here, natural log x divided by root x. And if I plug e squared into that, the square root of e squared is going to give me e. And the natural log of e squared is going to give me 2. So 2 over e is my relative maximum. Now, when I went on to the second derivative, I started from this moment right here, where I had simplified the best I could before looking at what makes the first derivative 0 undefined. So I'm using quotient rule, and here we go, because away we go. All right. Low 2x to the 3/2 power. There we go. So low d high, because the derivative of 2 minus natural log x is 0 minus 1 over x. Low d high minus high d low. For the d low, I'm taking the derivative of 2e to the 3/2, so I'm getting 2 times 3/2 x2. I said e when I should have said x, but anyway, x to the 1/2 power. And I get cancellation there. And then I take a look at what I have. When these two combine, I end up with negative 2 times x to the 3/2 times 1 over x. So that will be x to the 1/2. And then with this negative sign, I really didn't want to deal with it. So I went and said, you subtraction order, how about you just change and I'll turn that frown upside down from a negative to a positive. And then over here, I have times 3x to the 1/2 power. Always keep an eye out for factoring. Over this addition sign, we have a common factor of the square root of x, or x to the 1/2 power. So I'm going to factor that thing out, and that's going to leave me with this -2 plus, and then I'm distributing the 3 over natural log x minus 2, so I'm getting 3 natural log x minus 6. And combining a little further, I get 3 natural log x minus 8 for my numerator. And when x to the 1/2 combines in the denominator, I end up having to do 3 minus 1/2 to give me 5/2 for the exponent. And I've got my second derivative. Woohoo! Now, what makes the second derivative 0 and what makes it undefined? Keep in mind, though, we've got our domain of positive numbers only. The denominator is equal to 0 at 0, but that's actually the edge of the domain not included. So then what makes the numerator equal to 0? So I add 8, I divide by 3, and then if I have the natural log of x equals 8/3, I undo natural log by e to the powering, and I get that x is equal to e to the 8/3 power. Now, I want to make sure that my number line is only based on the domain. So I'm going to put a little open circle with a 0 and an arrow because the domain is limited to just that. I wrote my second derivative under here to help me with figuring out with each of these two intervals who's positive, who's negative. I need to pick some number in here that I can nicely plug in. And also keep in mind, I only need to know positive, negative. Because my domain is x greater than 0, my denominator is positive, so don't bother plugging into that. Save your breath. Plug into this x alone. And the easiest thing to plug into that is e to the power of something. How about we do e to the power of 1, because e to the power of 1 is smaller than e to the power of 8/3. If I plug that in here, I end up getting 3 times 1 minus 8. That's negative. Ba-boom. Now I need to pick any number larger than e to the 8/3, or think about what happens to this numerator if I plug an extraordinarily large x in. If I plug in an extraordinarily large x, natural log can be bigger than 8, bigger than 8/3. So I can do that, or I can try plugging in something like, say, e to the power of 10. If I decide I'm going to throw in e to the power of 10, then the natural log of that is 10. So 30 minus 8, I'm kind of positive. Now, this means that I am concave up when I am the number e to the 8/3 to infinity. I am concave down from 0 to e to the 8/3 power. And my second derivative changes sign at this number. That means I have a point of inflection at that number. Point of inflection. But e to the 8/3 is just the x coordinate of that point. I need the y coordinate. I've got to go back to that original function. That original function was natural log x over root x. So, there, okay, now you changed. Okay. Natural log x divided by the square root of x. If I have to plug in e to the 8/3 into both of these x's, the natural log of e to the 8/3 is going to be just 8/3. And if I'm taking the square root of e to the 8 thirds, really that's e to the 8 thirds to the 1/2 power, and I multiply the exponents, and that gives me e to the 4 thirds power when I multiply those exponents underneath the number 8 thirds. So at best I could say that the y value is, wait, silly me, and that's a 3. Okay, I can do this. Yes, I can. So the y value is 8 over 3 times e to the 4 thirds power. The best I'm going to do for saying the y coordinate without, what words am I trying to speak right now after a long day? The textbook, yeah, they wrote it as 8 thirds times e to the negative 4 thirds. Same thing. And then they just kind of approximated it. But there you go. There's 2 really lovely problems. And I hope you enjoy tonight's homework. Hee 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 hee. I guess I shouldn't laugh. I'll see you tomorrow.